Hello, everyone. Let's get started because the schedule is kind of tight. And it's my pleasure to be the MC of this session. I'm Vincent Chan, the Joan and Irwin Jacob Professor at MIT. So my job is to introduce the speaker, but today he is the second most important person I have to introduce. The most important person I have to introduce is his wife, Joan, who is here with him. And notice my chair is Joan and Irwin Jacob Professor. You know who's ahead. Oh, you certainly know. I'm going to give an introduction to Irwin, and with a little bit of my own slant to it, because he and I somehow crossed paths or virtual path several ways in the last 40 years. So Irwin actually is he received his bachelor degree in electrical engineering in Cornell University. I believe he started in the hotel school as well. For a year and a half. And incidentally, Cornell University Hotel School is the best hotel school in the world. It has exquisite food. The reason I know is my first job after I graduated from MIT was an assistant professor at Cornell. And I came back. Oh, you didn't know this? Oh, after all this year, you didn't know this. Okay. I came back because my wife found a job in Boston area. So anyway, and after he got his bachelor, he found out he's very good in math. Well, we knew that a long time ago. He went to MIT and got his doctorate in 1957. He got his Master of Science, and in 59 he got his doctorate. And he currently holds 14 patents in CDMA. And then he was faculty here and assistant associate professor from 66 to 72. He wrote a very important book with Jack Wollstonecraft called Principles of Communication Engineering. Actually, I was a grad student after Irwin left MIT, but I got to teach his class using his book, and that's when I found out that it was a really good book, and that's after I taught that, I think I finally know what communication is all about. So that's my connection to Irwin, with virtual connection without seeing him, but I taught from his book. I recently bought 6 copies of his second edition of his book, and somehow he has leaks. I think my students, some of them here, had taken all of them away from me. So I have an old copy, though. Anyway. Keep buying. Okay, all right. How much royalty do you get? And after he went to San Diego, he formed 2 companies. The first one is Linkabit, and actually the first product of Linkabit, or sale of Linkabit, is to MIT Lincoln Laboratory. Is that correct?
I'll touch on that.
Oh, you're going to touch on that. I won't steal your thunder. Yeah, I was the head of that division, and he delivered the first piece of hardware to that division. I was hoping Chuck Neeson, who was the group leader in that division, was here. He promised to try to come here. And you know Chuck, of course, yes. And Barney was the assistant division head, who I succeed later. Anyway, so that's our connection without actually knowing each other. I'll let him tell the rest of the story about that. Then he sold or merged with Maycom, with Linkabit, and then he formed Qualcomm. And we all know about how Qualcomm actually develops further CDMA and become a giant in wireless communication, not just in the US, but worldwide. So he is now the CEO emeritus of Qualcomm, and I think his son is now the chairman. Yeah, right, okay. So he has received many honors, but I would pick a few that would be actually that I would highlight. One is National Academy of Engineering and also the American Academy of Arts and Sciences. He got the IEEE Alexander Graham Bell Medal in 1995, and he got the National Medal of Technology Award which is the highest award bestowed by the President of the United States for technical achievement and commercialization of technology in 1994. It must be under the Clinton administration. I'm going to skip many of his honors because so many of them. He got the IEEE Medal of Honor in 2013, and he got the Distinguished Technion Medal in 2013. Technion, for those of you who are not in communications, is one of the giants in this field, and that's quite an honor. And then, to skip to the last one, he got the Carnegie Medal of Philanthropy in 2015.
With Joan.
Huh?
With Joan.
Yeah, with Joan. Okay, that's great. And with that, talking about philanthropy, he had actually been very generous in giving a gift to MIT, endow a presidential fellowship to the tune of $30 million. There were 14 presidential fellows per year appointed, and some of them are sitting here. Can you please stand up? Oh, you're dispersed. Oh, okay, all right. So this in particular, actually, MIT has about 100 presidential fellows. This particular fellowship is mostly for communications and networking, so Irwin helped us to feel very important at MIT working on communications and networks. So here's Irwin.
Thank you. Well, it's always great to come back to my, whoops, there we go.
Just going to press your wire a little bit.
Okay. Good. Always great to come back to MIT to, I read about it so much, to just see what is really happening here and all the excitement that's ongoing. Today, we actually brought back 10 fifth grade students from New Bedford who are touring here while I'm giving the talk. And we did this again last year from New Bedford, Massachusetts, my hometown. And when we got done, Joan asked them where they'd like to go to school when they graduate. They all selected MIT. Hopefully 1 or 2 may end up here, so that would be great. In any case, it's always fun to be able to do that. It's called the Shannon Lecture, and that ties in quite a bit with my career. Claude's had quite an influence over the many years. When I came to MIT for graduate work from Cornell, I had previous to that a very good course in EM theory and antenna theory, and thought that that would be my area of majoring. But Claude was on the way here to MIT from Bell Labs, and there was this huge amount of excitement about information theory. And it was contagious. So when I came, I immediately became very interested in information theory and communication theory. And that, of course, has impacted just about everything I've been able to do since. The various faculty here were quite interesting. I do remember not getting an undergraduate course from Claude, from Shannon, but he gave graduate seminars. And one area I remember quite clearly was seminars on source coding. And at the time, that wasn't quite as much known about it as channel coding, although he had always been interested in it. But of course, now with all the wireless communication and how do you compress voice and then how do you compress video, et cetera, and various kinds of data these days, it's become more and more important. And so a very early exposure to that again has proven very valuable. I was asked to be on join the faculty when I graduated, which was also great. One aspect, I guess, wasn't too great. I think I was paid $5,500 a year because being on the MIT faculty was, enough of a reward. I did supplement that by consulting, including some consulting at Lincoln Labs, so that went ahead very well. but was asked with Jack Wozencraft to teach a senior level course on communication theory. And at the time, information theory was considered to be applied mathematics with not very much practical use, and that was clearly going to change. And so we decided to try to put together a course that did give some of the theory, which is crucial, but then be slanted toward the fact that it could become very practical. And so that book has existed for quite a number of years. It was a wonderful experience writing a textbook, taking huge amounts of information, material, and kind of compressing and still being able to do it in a way that can be understood. So it was very valuable to me, perhaps hopefully valuable to others as well. One aspect of that was in explaining things, was that the Shannon had a limit, a low limit and upper limit on the energy per bit to noise level, EB over N0, that one, at least you had to provide that much and you could get very close to it, was kind of the Shannon theories. And at the time, it didn't seem too critical in most areas, but satellite communications, clearly, since satellites can have a limited amount of power, that EB on N0, being able to keep that at a low level, that was important. I'll come back to it later, but of course what then became very important in cellular communications, and particularly with CDMA, to keep interference levels down, you want to be able to operate at very low EB on N0s. And so that concept that I first started worrying about back when we were doing the book and teaching the course has again turned out to be very influential. You can never tell when these areas do come up and become rather critical. And another aspect in the book was trying to explain modulation, and then we got carried away and went beyond binary and and had, arrays of signals. Again, not thinking that that would ever turn out to be particularly useful, but of course now with the higher levels of modulation, being able to get the bit rates way up there and find ways of properly receiving them, that itself has become important. So it's funny the way you work on some things early on, and then at some point they do, in fact, turn out to be useful as long as your memory is good, which mine these days is not quite as good anymore. And so the time teaching at MIT was indeed very, very useful. But we took a year's leave of absence for our one visit to California and went out, spent 9 months at Jet Propulsion Lab, came back here. While we were out there, noticed San Diego was a kind of pretty city, and Berkeley, Santa Barbara. Came back here, and just after coming back, a former professor at Cornell contacted me and said that he's going out to start be part of a new school in San Diego called University of California, San Diego. And would I come out to help start engineering? And remembered San Diego, but family, friends are all here on the East Coast at the time. And so we turned it down. And I often tell the story, we were unhappy with that decision because we really did like California, and this idea of starting a new university and being able to grow things was intriguing. Second day, very heavy rainstorm, going from here over to the subway, got soaking. The subway only went as far as Harvard Square at the time, got soaked again waiting for the buses to go up to Arlington where we lived. Came in our rented apartment, soaking wet, and Joan read to me a description of a home. And I said, that sounds wonderful. We've been looking for a place around Boston to buy. Let's go look at it tomorrow. She said, there's only one problem. It's in La Jolla. Called up and said, well, if that position is still available, we're coming. So crazy little things can make such a difference in your life. You kind of follow your instincts occasionally. And so after being here on the faculty 7 years, off to the West Coast. While I'm thinking about it, let me mention why I started out in the hotel school there, and then I'll return to the West Coast. grew up in New Bedford, went to New Bedford High School. My high school counselor, when I was preparing for college, and I was, of course, thinking hopefully getting into MIT or some other technical, good school with good technology education, he said, there's no future in science nor engineering. And nobody had been to college or had a feeling for whether that was outrageous or not. My folks had a small restaurant at the time. They said, oh, you have to go to Cornell to the hotel school. And that's how I ended up in the hotel school at Cornell, which lasted for a year and a half, and then decided maybe there is a future in engineering, and switched over. Luckily, Cornell let me do that, and so that all did work out. Coming back to a trip back out to California, because of having published a book on digital communications and all of the firms in Southern California, and actually Northern California, that were in various aspects of communications, there were all these requests for consulting. And normally one consults a day a week. And so I happened to mention that to two friends from the UCLA faculty, Andy Viterbi and Lenny Kleinrock. And they said, oh, let's start a company and share consulting. And so that's how the first company called Linkabit started. So there may be some budding entrepreneurs here that have thoughts and plans and put business plans together. This was none of the above. We decided we'd start and share some consulting. But it began to grow fairly rapidly, and decided I better take a year's off. And by the way, some of the early employees, luckily, were some MIT graduate students who had gone out to finish writing their theses with me in San Diego, be able to hire and provide some really outstanding staffing to get us really up and going. So in any case, so I took a year's leave from teaching to get Linkabit organized because it had grown so much. And that turned out to be great fun. I can recommend that highly. But I had to rationalize why leave teaching. Don't listen. Why leave teaching? And I've been teaching theory for many years. And of course, there's always this issue. Is the theory useful for something? Why don't you teach me something that I could use tomorrow? And which, the right balance is fine. But here I thought, okay, I can show that the theory indeed does have great value. And so that was a rationalization for leaving academia and going into business, which then turned out to be great fun. There was a mention of working with Lincoln Laboratory. So one of the early projects had to do with building a satellite terminal. I won't say how we got into that, but a satellite terminal initially for the Air Force, although it was picked up by ultimately all the services. And at the time, one didn't have individual CPU chips. There were ALUs and register chips, et cetera, but not a single chip. And in puzzling how to do this terminal, we came up with the idea of using a processor that we'd assemble ourselves, but memory was expensive. And so how should you do that? Let's have only a few instructions. And so came up with what about a decade later was called the RISC processor, and which of course now is fundamental to all mobile communications for being very efficient as far as use of energy. Designed our own processor, multi-stack, so it could easily do subroutine hopping. And we started to implement a modem initially to go with Lincoln experimental satellite, LES 8 and LES 9. And we had a contract, I think, from Wright-Patterson to go ahead and do that particular work. And we were going ahead, designing our own small units. And then the Air Force came along and said, oh, we've got this other AFSATCOM satellites. Could you make the terminal do that as well? And of course, we said, well, it's programmed, so we ought to be able to do that without really taking a hard enough look. And so we accepted that. So it became called a dual modem for dual different satellite systems. And we went ahead and built that, and we're building it. And a couple of stories on that one. One of the good things about having been involved with academia and then a few companies is you have lots of anecdotes to talk about. So we were putting together the LES 8.9 capability, programming that into the unit, and suddenly got a call from Lincoln Laboratory. Now, Lincoln had been doing their own terminal, and so this was going to be a later backup follow-on. We got a call that next week they're shipping LES 8 and LES 9 down to be launched. Could you bring your terminal along and see if it's compatible? So worked the last couple of days, 24 hours a day for a couple of days to get the software checked out and tested a little bit. Got on a commercial plane, carried it on my lap back to here to Lincoln Lab. Got interrupted by a major snowstorm and ice storm, and the car wouldn't start. Finally got to Lincoln about 10:30. And unfortunately, at Lincoln Lab, I don't know if it's changed, 11:30 is lunch. So we wanted to go ahead and at least be able to hook this up to the satellite. It had a forward link from a command post to a mobile, to the airborne unit, and another one back from things, and those two links were different. So I said, well, let's at least test the forward link. And they said, well, we'll turn off the frequency hopping, we'll turn off this. And no, let's go try it. So we did, and just before lunch, the typewriter didn't have very good terminals at the time, that the teletype started typing away. Forward link worked. Down we went for lunch, had lunch, came back up, let's get the reverse link tried out. Reverse link first tried, didn't work. And we began to look at it. Well, Lincoln Lab, I hope you've done things better ever since, but at the time, all the documentation was handwritten. And it turned out Lincoln had read some of the numbers in a matrix incorrectly, and so it was their problem that they get fixed, which they did. Now the reverse link worked. And so Paul Rosen was the department head at the time. So I called Paul up to be able to show, hey, this thing's working. And Paul, very suitably impressed, he said, I've been telling people for years that you didn't need a PhD to build something designed at Lincoln. And I said, well, Paul, that might be right, but you can't prove it by us. So in any case, luckily, that all did work. It turned out that the Lincoln terminal wasn't ready. I'm not sure if it ever did get working. Yes. Right. One other story along those lines is, I have to be careful here. On the Air Force version, there was an encryption algorithm that had frequency hopping for both multiple access and anti-jam. And so it had an encryption algorithm to generate the frequency for the next hop, the code for the next hop, and had to do so every 5 milliseconds. So before you start the mission, you enter a code, and then enter time of day, and then it counts and gives you the codes. The way the Air Force specified the algorithm at the time, things luckily have changed a bit, was a book of circuit diagrams, flip-flops, gates, matrices, the various memory units. And that's how you made it. And luckily, they did have, at the end of it, if you put in this code and this time sequences is the code you get out. Well, I kind of worried about that for quite a long time and realized finally that it was designed in a way that put the code in, do a lot of crunching, prepare the right matrix, and then each time you put time in, it was very quick to generate the code from the time of day. So I won't say exactly how it's done, but you can probably figure that out. And so went ahead and programmed that up. A few months later, there was a design review, and we were competing with a fairly major aerospace company for this contract. And their program manager came over to see me, and he said, there's a rumor going around that you're doing this encryption in software? And I thought and said, well, be truthful. I said, yes, we are. Well, they had built it using this hardware design. They used what was then called echo-coupled logic, ECL, which was the fastest available. They still couldn't go fast enough to meet one of the specs, which was if you suddenly introduce a new time of day, getting the code out within 3 seconds, because just couldn't go fast enough. So he said, and I understand you can meet the 3-second requirement. I said, yes, we can. He looked at me and said, you're a liar. Which prepared me for a number of things that always happen in the future, in particular with CDMA, where there, and I'll come to that shortly, there are always these kind of claims. But we did win the production contract, and we built lots of these units. As far as I know, they may still be operating just by upgrading the read-only memories. Yes, you can add additional satellites or accommodate different satellite capabilities. And so that was kind of a fun project. And then, of course, the fact that it was based on risk, that's turned out to be very useful to us in the future. Let me mention one other thing, actually two, but that did a Linkabit, the first company. There was HBO, which everybody knows, was sending their signals from satellite to cable heads to distribute them by cable system. And they decided they better scramble those signals. They were being sent in the clear. And so they put out a bid for people, a proposal for how do you scramble these signals to the cable head. Well, in any case, we won that and started designing a unit. We're all ready to go into production on a unit to go to the cable head. So it could be a professional unit, heavier, more expensive, run by a technician, et cetera. When I had my first significant political experience, and by the way, if you're in technology and get into companies, the politics really end up coming first, but in any case. In this case, just warning you a little bit, in this particular case, there was a group of backyard dish owners, and they went to Congress and said, look, we've been receiving HBO all these years. We've got huge investments in our backyard dishes. We're willing to pay something for descrambling, but you've got to be able to, HBO has to allow us to buy a descrambler. And so suddenly we had to build something for the home unit as opposed to a professional unit. Well, how do you do that? You needed chips. Today, you wouldn't think about that particularly twice. At the time, there was no commercial software available for designing and testing chips. And here's where MIT, among others, come in. Kind of seeing the future, I had sent one engineer up to spend a term at Caltech, where some of the early computer design was being done, chip design, and another person out to spend some time at MIT, University of Washington. And we brought back some software, and we're getting ready to do some homework problems on how do you design chips. When suddenly, for this descrambler, we had to design 3 chips using untested software and be able to test that on the computers as well. Amazingly, all 3 chips worked the first time. It was just one of those very lucky breaks that did happen. Convinced me that indeed this was going to be the future. There was another interesting thing that actually happened. So we ended up with a home descrambler, going to be a big business. Where should you manufacture that? And it turned out at the time in Puerto Rico, and these are all the considerations if you're going into business, things you end up worrying about. If you're going to Puerto Rico, if you're going to manufacture, in Puerto Rico at the time, the pharmaceuticals had arranged the deal that any value add in Puerto Rico would be tax-free sold in the US. So we went and built our factory in Puerto Rico, and that ended up being a tax-free business. So it was a gold mine. Unfortunately, about that time, we had sold the company to MACOM, merged to MACOM. The person who was running MACOM, I was the executive VP, was another MIT PhD, so that was kind of a good grouping. But he remarried, moved to Florida, the board lost confidence, whatever. And so they had replaced him, and I knew then it was getting time to leave. Retired for 3 months, debated whether to come back to teaching, which would have been fun, but there were 6 others that had worked with me at Linkabit that said, let's start another company, let's start a company. And so that's how Qualcomm started, again, without any plan, without any product, no spreadsheets or anything else of the type. And by the way, in neither company any venture capital, which made life a little simpler. But in this case, I knew that if we did succeed, did not want to sell, we were going to just keep the company going ourselves, which is a good lesson to have learned. We didn't have any product in mind, as I mentioned. We had the same strategy. We're going to try to be innovative, not try to do something a little better. What can we do that was significantly better? And Hughes Aircraft was in the process of submitting to the FCC a proposal for a mobile satellite system. At the time, they didn't have easy mobile communications. This was really before cellular was widespread. And they wanted to do it with a satellite. They hired us to review their proposal, which was relatively traditional TDM, TDMA, FDMA, up-down links. And off the second meeting, driving back down, it suddenly occurred to me that perhaps CDMA, code division, might be a better approach. And why was that? Well, if you're by yourself, a single mobile user, there's times when you're listening, there's times when you're pausing between speech, et cetera. There's time when you're not using the channel. With traditional technology, particularly satellite delays, you can't give up the channel and then get back when you resume talking again without losing part of the speech. With CDMA, the capacity limit is set by all the users that are using the system at any given time, the average amount of noise, of interference that they're generating. And so you stop talking, you stop generating interference. Actually extended that if you're talking slowly or in a way that's easily understood, you can compress the vocoder and send less information, so variable rate vocoding. That with CDMA, that might make the difference to get greater capacity. And so we followed up on that. It turned out there were other uses, again, with spread spectrum, that's very good anti-jam qualities. With cellular systems and satellite systems, you have multiple antennas, and the approach with TDMA or FDMA was not to reuse the same frequency on spatially adjacent channels because they interfered too much with one another. But with CDMA, you could do that and you could stand the interference. So we said, okay, this sounds great. Went back, described it to Hughes. They were not believing us, but interested. But then it turned out that was going to take several years before the FCC would ever rule on it. It did take over 3 years. And they put a consortium together. So they stopped funding this particular consulting job. Turned out to be lucky. We were still too small, didn't have the money to pursue CDMA, and we were close to another product, which was providing a two-way communication system for the trucking industry and putting a small satellite terminal, it wanted to be continent-wide, a small terminal on a truck and providing two-way communication and position location. And there were a couple of problems, 3 perhaps. One, the satellites that were available then were designed for feeding very large dishes for TV. And I should have mentioned that at Linkabit we also developed the very first VSATs, very small aperture Earth terminals. And so they were being used for those, so those were a few feet at least in diameter. And the ones we designed had coded signals, et cetera. And so there were a number of VSATs out there. How could you have a small terminal with taking all the power from a transponder to drive that? And again, spread spectrum approach. So we went to spread spectrum. Need an antenna. how do you get an antenna that you can put on a truck, have roughly 19 dB of gain at KU band? And that was puzzling. And again, my EM theory from Cornell came in very handy when I realized you could stick a probe up into a waveguide that would rotate, have a flared opening, and that would form a pencil beam, a fan beam, and rotate that and come up with an algorithm for the rotation. And when you look again, if you went under a bridge or through a tunnel, when you walk on, etc. And so we came up with this antenna. It was an interesting challenge because JPL at that time had a contract out for a mobile antenna before they were trying to get into commercial businesses for the trucking industry. They were shooting for a $50,000 antenna. We were shooting for a $50 antenna. And luckily this approach, building everything out of plastic, by the way, and just coating it in the right place, did work. And so we ended up with the antenna. We had one other problem though. I mentioned the downlink, we're using the full satellite power and using it spread. So we had a 1 megahertz direct spread and then frequency hopped. And we wanted that to be able to work and not interfere with anybody. We didn't have a prime use of the frequency. The FCC would only give us secondary use, which meant you could not interfere with anybody that was already around. Well, we thought, well, the VSATs that we had designed had coding, interleaving, no problem. But it turned out that people had come out with cheaper VSATs. And as a result, the interleaving coding that we assumed would be there weren't, and therefore the frequency hopping every 5 milliseconds would cause trouble for those cheaper VSATs. And so the question was, what can you do? And we puzzled, and luckily one of the engineers, Klein Gilhausen, said, I think I've got an idea, and then we pursued it. The satellites were mostly being used for TV transmission. Well, how did they transmit TV? They had a signal, roughly 4 to 6 megahertz wide, that they'd sweep across, back and forth across the band. So we made a digital signal that swept back and forth looking like a TV signal, figuring anything that's out there had to be compatible with that. And indeed, that did work. So we thought we might be at a dead end, but that was a way through it. We had a number of battles as far as then going out to the trucking industry. We had that problem solved. We needed position location, by the way. And how do you do that? Well, at MIT during World War II at the Rad Lab, they had come up with LORAN. And that was still in operation over parts of the US, so we thought we'd use a LORAN receiver.
We're turning it back on. It was a GPS disablable.
Oh, okay. The one trouble with it, though, when you get near a filling station with neon lights and so on, it would kill it. And it was not that accurate. And so, and this was before GPS satellites. But we had, on the communication side, a 1 megahertz signal. It was being frequency hopped around. Said, okay, let's put a 1 megahertz, just a 1 megahertz signal, so it's cheap, on a second satellite, a reasonable angular separation. And then ever so often have this antenna go over, look at the second signal, grab it, get a time measurement, and come back again. And so we set up, in some sense, our own GPS, mostly getting the communication signal, but occasionally going over, grabbing a second satellite. And that worked like a charm until GPS became available. We sold that system, therefore had a cash flow coming in, and went back to looking at CDMA. Now, it was interesting. Cellular had been invented at Bell Laboratories, and I think it was in 1980, AT&T had hired a company here in Boston to do a study to decide whether it's a business that AT&T should pursue. And that study, the result of it was that there might be just a little under 1 million subscribers. This was in 1980, a little under 1 million subscribers by the year 2000. AT&T did not go into the business. One piece of advice, never listen to consultants. There were 100 million subscribers by that time. So AT&T missed on that, unfortunately. But the industry, early on, so this was now 88 when we came back. We started the company in July of 85, so this was about September of 88. Came back to look at CDMA. The analog transmission, the first so-called generation, had grown. People were worried about whether or not one had enough spectrum. The quality wasn't very good being analog. And so what can you do? Let's go digital. People around the world had looked around about using CDMA, given up on that approach, decided to go with TDMA, debating between TDMA and FDMA. And by the way, the very first commercial TDMA wireless phone we had done at Linkabit for a company. In any case, TDMA did win. And so in January, there had been a vote of 89, go with TDMA. About March or April, and it was bitter, by the way, the debate. About March or April, we felt confident enough that CDMA really was worth trying and that we had solved a number of the problems. What were the problems? Well, with CDMA, you have what's called, many of you may know this, but anyway, a power control problem. That is, you want to not be shouting in somebody's ear because you drowned out everybody else. You want to just make sure there's just enough energy reaching the receiver to be able to be properly demodulated, decoded. And how do you ensure that as the device is driving around, goes behind a building, et cetera, and people had attacked that problem and not been able to solve it. And we came up with a MIT-type solution using some control theory as well. Now, since the engineer's here, I'll touch on it very quickly. Came and said, okay, the signal that we're receiving, if that suddenly goes down, it means that we've gone behind a building. If it suddenly goes up, we might have come up into the open. And so the first level of control should be just listening to the received signal. And it goes up, we go down, and transmitting, and vice versa. That's okay, except that we're receiving and transmitting on two different frequencies. So it's a rough correction, but not a perfect one. So then you need a second level correction that still was fairly rapid. And so we would set a threshold. And if the received power is above that threshold, we reduce our energy a little bit. If it's below the threshold, we can raise our energy a little bit and adjust that. That works very quickly because you can measure power very quickly. But how do you set the threshold? Well, that you have a little more time to work on. And so we had coding and decoding. We'd look at the number of corrections being made by the decoder. And if there are too many corrections, we better transmit more power, or too few, less power. So we were able to get kind of a three-level power control, and that worked like a charm. So that was really one of the very hard problems solved. Another had to do with multipath. Radio waves bounce off all kinds of things. You're getting several copies of it. Well, this was a megahertz direct sequence, so you can resolve those down to under a microsecond and receive each one independently and combine them together, and you end up with an enhanced signal rather than a degraded signal. So that was a second solution. And the third one was, how do you hand off as you go from one cell site to another, or even within a cell site, among multiple antennas? Well, there you could do the same kind of thing. That is, it's almost like multipath. You're listening, you get another signal, and you can listen to both of them for a little while, get an enhancement that way, and then as one gets weaker, you just stay with the stronger one. So you're doing a soft handoff between. So all these looked very good. Went back to the industry and said, look, we've got solutions to your problems. With CDMA, you can get, we think initially, maybe 10 to 20 times the number of subscribers that you can get per antenna per megahertz than you could with analog. With TDMA, which had been selected, at best you could get a factor of 3. So the carriers were excited because they get that many more subscribers. But nobody believed us, of course. And so the next step, you had to go ahead and build a quick mobile unit and a few base stations to demonstrate, which we did in the next 3 months. Brought everybody in for a meeting, demonstrated that we had solved the problems, and in particular, some of the carriers got excited. The manufacturers who have been working on TDMA weren't too excited about it. But the the mobile unit required a van to drive it around. And so how do you get that squeezed down to a commercial-sized phone? And the answer to that was you need to develop chips. Well, we had done that once before at Linkabit, and we had actually done a little bit of that in a project with you on a different government program. And so we had developed that, and the industry had moved along quite a bit. And so we had to develop chips for both the handset and for the base station. But that's an expensive proposition. How do you raise money? And you can be innovative, I often say, not just with the technology for the product, but for the way you do business and indeed for your business plans, et cetera. And so came up with an approach for licensing users where they would pay us an upfront fee, and should this ever become commercial, a small royalty per unit sold. Nobody paid attention to the latter aspect because they didn't expect any of these to be sold. And the carriers, because they said if this does work, we get that much more use of our spectrum, put pressure on for people to sign the licenses. So we did get a number of licensees signed up. Now it's several hundred. And that gave us the money to go ahead and develop the chips. So in 2 years, we developed the chips, had a phone, had base stations, brought everybody back for a demonstration. The group of cellular operators said, okay, we'll go ahead with a second standard above and beyond TDMA. But to get there, they wanted to have a comparison test. And luckily, TDMA really didn't work all that well. And so we had great audio of CDMA at both ends of the link. And the TDMA people at this demonstration went first. They demonstrated it was supposed to be a commercial system. It sounded terrible. CDMA sounded wonderful. The industry decided, okay, we can have a second digital standard. That took another year and a half, which was very fast, but we had huge amounts of data available on CDMA. And so we ended up with a standard. The net result was that the first system went commercial with CDMA in Hong Kong in about October of 1995. So it was 7 years from the time we started looking at CDMA seriously for cellular until the first commercial system. So it was quite an interesting period, but very effective. Why Hong Kong? Just that there were lots of users there. At the time they couldn't afford offices, they'd be on the street with their cell phones, congesting the limited spectrum. CDMA would give you more use, and so it was done there. Second, we ended up in South Korea. Why South Korea? We'd gone there. I talked with the government people, with the companies, government laboratories. South Korea at the time didn't have much of a commercial electronics business. So again, politics, governance. They've been trying very hard to get ahead of the Japanese, but they're always lagging behind. They could only compete on cost. So here, Japan had gone with TDMA, was an opportunity if they went with CDMA and it worked, and this was early in the 90s, they could be ahead of the game. Well, indeed, it did work. And of course, now Samsung and LG are two of the major manufacturers for cellular equipment. Before then, they had zero market share. And so that worked out. One more such story, I had to break into China. And so I'd given a lecture there in the beginning of '92 on CDMA, and there was a large audience, a lot of interest in CDMA, but it turns out one of the ministries controlled the frequencies, and they had been very close to European operators who had, by a government agreement, could only use GSM, which at the time was TDMA based, third generation CDMA based, but then was only TDMA based. And it took 10 years really to work out a reasonable deal that was useful to us and acceptable to the government to be able to go ahead and get CDMA in. Actually, we got that, reached that in about 8 years, and that itself was a story. I was on an advisory, still am on it actually, an advisory committee for Tsinghua University, and Zhu Rongji, the prime minister, premier at the time, had founded that particular school and had organized this committee. So I managed to buttonhole him after one of the committee meetings saying, we're having all these troubles, this is great technology. He was also an engineer. He could understand some of it. And so we came to agreement if we did certain things to make it really suitable for the Chinese market to the chips, that he would help get us in. And so about 8 years, we finally did get ready for the manufacturing companies to sign an agreement with a second Chinese cellular company to be able to use CDMA. And that was the time that the US dropped the bomb on the Chinese embassy in Belgrade. And that stopped everything, as you would imagine, for a year's time. Got that settled, came back almost ready to sign again when there was a collision between a US reconnaissance plane and a Chinese jet. That stopped things for another year. And finally, 10th year, we did get things signed. One of the interesting aspects of that is that, I hope I'm not discouraging anybody from going into business, but one of the interesting aspects of that was, you have these Wall Street analysts who claim that they understand the businesses, et cetera, et cetera. And so they wrote that, why was I bothering going through all this effort to be able to bring cellular, a new form of cellular to China? They already had 250 million subscribers. That was the entire middle class. There was never going to be a market. Luckily, that has, of course, turned out to be wrong. It's turned into a great market. In any case, so CDMA went ahead, second generation, huge religious wars. One last story on that. There were two professors at Stanford that kept claiming that CDMA violated the laws of physics, that would never work. They even made the front page of the Wall Street Journal that my hype was costing people fortunes. And so often now I will not infrequently give talks at Stanford, but I point out that CDMA works everywhere in the world except within a 10-mile radius of Stanford. So get even a little bit on that score. Second generation, the big battle. Third generation, everybody went with CDMA. So all third generation, because it was data and voice, and so internet access became very critical. And CDMA was, at that time, by far the best solution. So everybody threw up their hands and decided, OK, we'll go with CDMA. And so all of the CDMA, so there's probably about 3 billion users at least 3 billion around the world on CDMA at this point. And that is the prime way of accessing the internet most places. Now, as you know, we've gone on to a fourth generation, OFDMA, with enough processing power and some inputs from work here at MIT as elsewhere. And you can't ever hold still when you have a company, so you have to keep running ahead. So we ran ahead also on the FDMA, so we're the largest by far. Qualcomm, no longer there really. The largest provider of OFDMA capabilities. And now we're getting ready, of course, for a fifth generation. Well, what's that going to be? Well, it's going to be a number of things. It's going to be a number of higher frequencies because, indeed, spectrum's limited. Everybody wants video on demand. That takes a certain level of bandwidth. Even more than that, now the cell phones have enough computing power to be able to receive 4K, not just HD TV, but Ultra HD TV, take the videos and show them. But how do you get that to a large screen? And so now we're going to 60 gigahertz type transmissions from the phone. It's already on chips to be able to provide that kind of data link. And of course, a whole set of Wi-Fi frequencies as well as different frequencies. So the whole picture gets more and more complicated. And then how do you put together large cells, small cells, microcells, et cetera, and not have the user have to worry about any of that? So I think all that's coming together in what one might call fifth generation, that you can handle all the different possibilities seamlessly for the user, give them the most efficient approach, least load on the networks, and be able to accommodate everything that's going on. So this whole area continues to move ahead. Let me finish by just mentioning some of the other exciting things that are happening, namely the impact on everybody's lives. And so we began to recognize this early on, and we looked around and One of them was helping fishermen, helping farmers, obviously environmental effects, what crops, what fish would have the highest price, where should you bring them to market, and so those have turned out to be very helpful. A variety of medical approaches, a number of which are being pursued here as well. Education, how do you use technology, finally after 30 years of saying it would be helpful, have now demonstrated that indeed it is very, very helpful. The wireless devices are becoming very important in each one of these areas, and so there's just a lot of excitement, and of course now the social media, a lot of excitement not just in the technology side, but also then in the applications. And back again in the China days, I was at a meeting with then President of China, Jiang Zemin, and he, in kind of a little informal conversation before the meeting started, turned to me and said, by the way, how many more generations do you think Moore's Law has to run? The last thing you'd expect to hear from a president of China, certainly of the United States, although lately we've had some very intelligent, at least one very intelligent one. I should say two, I'm be careful here. In any case, that was the question. Moore's Law has still continued to run, so we have probably a couple more generations. That gives us a lot more flexibility. What do you put on the chip? And that raised the issue of architecture as well. How do you architect the chips? What do you do about CPUs? You've got video processing, you've got display processing, playing games, receiving, of course, the GPS from several different satellite systems. Part of that's done in the hardware and the CPU and various special purpose processors. Some is now being done in extra little hardware add-ons. And so how do you put all this together in a very efficient fashion, given the flexibility that you have from Moore's Law? And so the whole area, in that sense, also remains very exciting. So very lucky, going back to Claude Shannon, being kind of directed into communication theory, information theory, and then being able to take advantage of that over the years, and it has been a great excitement. Thank you all.
So I just want to invite any questions from the audience. Before you think about a question, let me tell you something. Something never changed. I'm chairing the Defense Science Board Task Force on Communications and Networking. The problem is the satellite terminal on the ground. And one of the competitors that didn't make the crypto unit is having a problem. And I'm having a hearing of 4 of them tomorrow in Washington.
Oh boy.
They couldn't make the terminal cheap enough. They tried to charge the government $1 million copy, and they couldn't make it cheap enough. So you wish that Qualcomm is still in this business. I guess not. So any questions?
Have them take a look at using the chips that go in the phones.
Yeah, that's what I'm trying to get them to use commercial product, but they refuse because of some military requirements.
One of the fun things, of course, is on drones and robots.
Yeah.
Now more and more the chip that goes in the phone has so much ability to take inputs from sensors, from cameras, et cetera, that it's going on all those devices as well.
Any questions? Yes.
So you've been involved in a lot of different opportunities, from being a professor to a businessman. And what is the mindset you took to making these, I guess, life decisions? Because it seems like there were a lot of significant decisions that led you to where you are now and your success. So how did you think about that?
Right. I'm a great believer in being opportunistic. You can try to do strategic planning, longer term planning, but nothing ever quite works out that way. Things change so rapidly. And so sometimes an opportunity just turns out to be very appealing, and you decide to go with that. On the other hand, each step tends to be supportive of the next step. And so I often get the question, being an academic, how do you go into business? Isn't that just a huge difference? And so the explanation I often give there is, and also how do you set up the environment, is that having been a faculty member for us has proven to be very, very valuable. How does the university run? Well, first of all, lots of free thinking, lots of thoughts, lots of innovations. I mean, that's what you're trying to do. That's what you want to do in a company. How do you operate within that as a faculty member? Students come in, want to do a thesis, you have some ideas, they go off, work for a while, come back, get redirected perhaps a little bit. Well, same kind of thing in a company where you're trying to be innovative. And so in that sense, things were somewhat the same. But you also have to worry about finance and purchasing and human relations, HR departments, and other business-related type of things. Well, in a university, you have to worry about committees. And so I figure committees are half your time in one case, the business is half your time in the other case. At least in business, you can make a decision.
Yes. Can I ask a question? Actually, what you said was that maybe we have been teaching too long, look at naturally risk first. But what you said is somewhat scary. When you were trying to do the demo of CDMA, you said you have several months' time to solve several difficult problems. Those are the power control, the read receiver of one pass, the handoff. Each one of them is a difficult problem. And what if you don't solve one of them in time? Right? And the question is, do you have a backup plan in time, or if anything happens, would we have no CDMA today?
That came closer than you can expect. Yes. When you're, again, in business or in academia, you're always taking risks. And I think if you're not comfortable with taking significant risks, betting the company, betting your career, whatever, then you might be better finding some other approach for life. And so one needs to take risks, but one needs to also think them through. What's the downside? What's the upside? Is there a plan B possible or not? Sometimes you have to race ahead to find a way to make things work, which means you do some redirection. You know, your original path may not be exactly right. You redirect a little bit and keep moving. Dynamic programming as you're going along, it ends up being absolutely critical. But the approach we took was indeed, it felt as if we ought to be able to solve these, we ought to be able to implement. But that question came up because when we were building this demonstration unit, the whole world was running ahead developing TDMA commercial equipment. So we knew we couldn't take too long or CDMA would have to wait for another generation. And so we had to move very quickly. And so in September, I had to decide whether to send out invitations to bring people in to view CDMA at the beginning of November and be able to keep things moving ahead. And so I checked with a lot of the people working on the programs, and I had been involved with enough of it, so I had a reasonable feeling myself. And I would say probably 80% thought we better wait. But I had enough of a feeling, A, people are often conservative, and B, things were moving okay. And so we decided we'll send out the invitations, have a good firm deadline, which always helps, and we'll get this thing done. People came in, made a presentation on CDMA and what it was all about and what the demonstration was going to be about. I was all set to wave people, go out, some to the van, some will go to the labs, hear both sides of the call, et cetera, when an engineer in the back of the room started waving, keep talking. There is an advantage to having been a university professor. You can always talk for another 50 minutes. So I kept talking. And luckily, before the 50 minutes was up, just before, had a wave. It was okay to send everybody out. What had happened, we were using what were then experimental GPS satellites. It wasn't operational yet, as a time and frequency reference for the base stations to coordinate the various base stations. One had come over the horizon with a bug in it, threw us off, took us a while to figure that out, reset, and keep going. So if that had gone another half an hour or so, probably no Qualcomm.
Okay, all right. We need to stop here. That's a reception. reception after this, and Miriam has an announcement.
Yes.
Thank you.
Thank you.
Thank you all.
Thank you very much. So this is the penultimate lecture in our Boole-Shannon lecture series that has been going on once a month for the entire year. This is a joint effort among MIT RLE, MIT Physics, MIT EECS, and University College Cork. Our last lecture is going to be given by Professor Sergio Verdu from Princeton about the life and scientific contributions of Shannon next month. So I hope you can attend that last lecture, and there is upstairs a reception.
6th floor.
Yes.
Yes.
Thank you very much.
Yep. Thank you.